Hello everyone. Welcome to the Bangalore Theory Seminar Series. This week we are excited to have Sidhanth Mohanty as our guest speaker. Sidhanth is a PhD student at UC Berkeley where he is advised by Prasad Raghavendra. He is broadly interested in spectral graph theory, random matrices, and their applications in theoretical computer science. Today he will be giving a talk on local and global expansion in random geometric graphs. So let's welcome Sidhanth and all yours, Sidhanth.
Okay, thank you so much for the invitation to speak here. Thank you everyone for coming, and thanks for the kind introduction. So today I'm going to talk about this topic of high-dimensional expansion on random geometric graphs, and this is based on joint work with my wonderful collaborators, Siki Liu, Slee Schramm, and Elizabeth Yang. Siki and Elizabeth are also PhD students at Berkeley, and Slee is a professor at Stanford. So yeah, we can jump into the content of the talk right away. And also, if anything is unclear at any point of time, feel free to interrupt and ask me questions. Okay, so let's begin by introducing the basic notion of spectral expansion. So in the setup, imagine you have an n vertex graph G. And if it helps, you can also think of this graph as being regular. And the main object of interest for this graph is going to be its normalized adjacency matrix. uh, Namely the adjacency matrix where all the rows are normalized by the degrees. Now, this matrix has n eigenvalues, which we're going to denote lambda 1 to lambda n in decreasing order. Lambda 1 is always going to be equal to 1, and these eigenvalues are always going to be between -1 and 1. And the main quantity of interest to us is the second largest eigenvalue, which we call the spectral expansion. And we call a graph a spectral expander if the second eigenvalue is bounded away from the first. If there is a gap of at least some constant epsilon between the top eigenvalue, which is 1, and the second eigenvalue. And we are happier, the larger we can make this gap, the happier we are. And now, just to give you all an idea of why one might care about graphs where the second eigenvalue is small, let's talk about some properties that you get once you have a spectral expander, namely when your lambda 2 is bounded away from lambda 1. So first of all, if you take a random walk on this graph, it actually mixes to the uniform distribution pretty fast. And also, having a small second eigenvalue means there's no sparse cuts in the graph, and there's also no dense subgraphs. And these are all useful combinatorial properties that make these spectral expanders very interesting and useful objects. And they have several applications, such as to error correcting codes, to pseudo randomness, also in the construction of fault tolerant networks, um, in understanding instances of metric embeddings and approximation algorithms, and the list goes on. Okay, so now I told you what a spectral expander is, but now the question is, do they exist? Like I gave you a definition of an object, but how do you know what this object is? And let me bring up a very striking theorem of Friedman, which essentially says that really good expanders are everywhere. So in particular, let's say you take random deregular graph. We can call this random deregular graph G. Then with very high probability, the spectral expansion of this graph, the second eigenvalue, is at most something of the order 1 over square root d. So I wrote the exact formula here, but you should really think of this as being 2 over root d. And as depicted in the picture on the right, if you think of like the space of all deregular graphs as being some cloud, uh, and I mark everything that is an expander in red, and the ones which are non-expanders in blue, like the blue stuff is going to be a very vanishingly small fraction. Okay, so and actually, there's also many explicit constructions of expander graphs that are known at this point. For example, there's Cayley graphs, there's Cayley graph-based constructions, and there's other combinatorial methods, something called the zigzag product. Then there's a method of interlacing polynomials, and you can also de-randomize Friedman's theorem. Okay. So the point here is it's very easy to find expanders, and it's also at this point there's many explicit constructions known. But the object of interest in this talk is some sort of extension of spectral expansion. We are going to look for spectral expanders with more specific structural properties, and it's something that we call a two-dimensional spectral expander. So normally when people define two-dimensional spectral expanders or higher dimensional spectral expanders, they tend to use the language of simplicial complexes, which are certain types of hypergraphs. But I think I'm going to avoid all hypergraph notation in this talk, and I'll stick to graph. And as a result, some of the stuff that I say might be like at a very formal level, like somewhat inaccurate, but I hope that's fine, and I hope it does help like clarify some of the intuition. Okay, so now let's talk about what a 2D spectral expander is. So let's say I have an n vertex graph G, such as the one on the left. And one important notion for us is something called a link in a graph. So you should think of a link of a given vertex in this graph V as the induced subgraph of the neighborhood of this vertex. So here I chose this green vertex. The neighborhood of this green vertex is all the vertices that are marked in pink. And the induced subgraph on those 5 vertices marked in pink is a 5 cycle. So the link of the green vertex is a 5 cycle. So this is an example to illustrate what a link is. And here's what we call something a two-dimensional expander, a two-dimensional spectral expander. First of all, we want the original graph that we start with to be an expander. And in addition to that, we would also like the link of every vertex. So for each vertex, for each of the n vertices, you get a graph that is the link of that vertex. You want all of these n little graphs to also be good expanders. And actually, we remember in the definition of a spectral expander, we wanted the second eigenvalue to be bounded away from 1. Here we actually want them to not just be bounded away from 1, we want them to be bounded away from half. So this is what a two-dimensional expander is. Now this number half might seem a little bit arbitrary. So I'll spend the next slide explaining what the significance of half is and why half is an interesting threshold. But I think this is a good time for me to maybe have like a small pause to see if people have questions. Just to clarify stuff. Okay. Oh yeah.
So does 1D expansion, so this is a stronger property than 1D expansion, 2D expansion? Or are
Yeah,
there?
yeah. So
Okay.
for example, if you take a random graph, like a random deregular graph, and think of d as being a constant, it is a 1D expander, like we discussed earlier. But if you look at what the links are, like the local neighborhoods, so random graph is going to be locally tree-like. If I pick a vertex and let's say I draw like a even radius 20 ball or something, I'm very likely going to see a tree. So if I look at the link is just going to be 5 isolated vertices, and 5 isolated vertices are not going to give you an expander. So yeah, good question. I think I maybe saw someone else's mic flash, but okay, maybe not. All right, I'm gonna keep going then. Okay, so now I'm going to describe what the significance of this number 1/2 is. And this is going to come from something called the trickling down theorem. And actually, I think this is a pretty amazing theorem, and I'd say this is a reason I find like two-dimensional expanders an interesting object. So it says, let's see in your graph G, if every link has spectral expansion lambda, and let's say a graph G also happens to be connected, then the spectral expansion of G is at most some number which only depends on lambda. This lambda divided by 1 minus lambda. And okay, the reason I find this theorem amazing is you have a very local way to check for expansion. Each vertex, you just need to check what the neighborhood of each vertex is if you have a 2D expander. And if that neighborhood actually does indeed give you a good expander, like with this better than half expansion, then you do get that your whole graph is a good expander. Okay, I guess maybe the half thing still isn't clear. So notice that once lambda is smaller than half, this number, the bound that we get on the spectral expansion, lambda over 1 minus lambda, is less than 1. And notice once lambda is equal to half, uh, you get a somewhat meaningless bound. So this theorem is only meaningful once lambda is less than half. So that's why half is like the threshold of interest. And we see this is saying that the global expansion of G, like the spectral expansion of the whole graph G, can be witnessed very locally if the links are actually indeed very good expanders. So okay, now we have this theorem, and the next question is, well, okay, you gave me this theorem about graphs where links are very good expanders, but do such graphs even exist, or do such sparse graphs even exist? Oh yeah, and by the way, another thing is it also does imply like rapid mixing of a different kind of walk where you think of the walk as being on the edges of the graph, and I go from one edge to another if they share a triangle. But okay, this is a little bit of a tangent. Okay, so now the phenomenon of two-dimensional expansion or two-dimensional expansion expander-like objects uh, have actually had several applications in the recent past. Like one of them, for example, was to sample a random base in a matroid, such as say a random spanning tree in a graph. The analysis of that Markov chain actually relied on this trickling down theorem that I showed you in the last slide. And more recently, like some kind of 2D expander like objects were used, not exactly of the form that I defined, but they were used to construct locally testable codes and also to construct quantum low density parity check codes. Okay, so the question here is, are there examples of two-dimensional expanders which have constant degree? So earlier we saw that a random d-regular graph has even when d is constant is a good expander. So can you similarly find two-dimensional expanders of constant degree? And the answer is yes, but for a very complicated reason. Like there's these works of Cartwright, Soleil-Zook, Lee, Lubotsky, Samuel, like all the citations I've put here, which construct two-dimensional expanders using deep algebra. And yeah, the analysis does require a lot of like algebra and number theory, and the constructions themselves are also like pretty hard to visualize. Whereas this is actually in very stark contrast with expanders. Like if someone came to me and said, "Hey, give me like an expander," I'd say, "Oh yeah, try like a random d-regular graph." This is like a very easy thing to describe. But if someone asked me for an algebraic construction, I wouldn't know how to give them like one that is easy to wrap their head around if they want a sparse algebraic two-dimensional expander. So so the goal that we all started with was, can we get simpler constructions of such objects that don't use algebra, that are say more intuitive? And the main result in this talk is going to be some partial progress towards this problem. So okay, now let's start by investigating whether certain natural models of random graphs actually give you two-dimensional expanders. So what if you do the following? You you just sample a graph from GNP, and then you ask whether this graph is a two-dimensional expander. Here's what's gonna happen. Uh, all the links are gonna be disconnected unless this probability P in GNP is larger than omega 1 over root n. But this gives you a graph with average degree larger than square root of n. This is like way bigger than constant, which was what was needed for like one-dimensional expanders. Like if you look at random 5 regular graph, you get an expander. But here we are saying if you take a GNP, you need square root n degree. So this is really dense. And then there were other similar models that people studied, but all of them ran into this root n barrier, where they need a degree larger than square root n to have connected links. So so they really were not two-dimensional expanders in like a very dramatic sense.
Siddhant, could you
Oh
go
yeah.
back to the random construction and tell what the problem is there again? Yeah.
Okay. So like uh, so let's say you take a graph from GNP, and
Sure.
now you ask, is this graph a two-dimensional expander?
Okay.
Uh, so now here's the thing that's going to happen. Uh, let's look at the link of one vertex. All right. So a single vertex is going to have p times n neighbors.
Okay.
Okay. Now among these p times n neighbors, for every pair, you put in an edge with probability p.
Okay.
So if I pick a vertex and if I look at its degree within the link, uh, there's pn vertices in the link, and a vertex has p chance to connect to each of those. So the expected degree is p squared times n. But now we want we want the links to be expanding, but to be expanding at the very least, they need to be connected. So the expected degree of a vertex better be at least 1, because if it's not 1, then there's probably going to be a bunch of degree 0 vertices, and that's going to mess up your construction.
Right.
So, but now for p squared n to be at least a constant, you need p to be 1 over square root n or
Okay.
larger. But if p is 1 over square root n or larger, the degree of your graph is going to be square root n or larger.
Right. That's not a sparse. Okay.
Yeah, and that's like really not sparse. So that's what you want to do better. Yeah, I'm not going to get into like these alternate models that similarly also hit like root and barrier for similar reasons. But I can say this model of random graphs that we try to analyze, which is this random geometric graphs, and we do not get constant degree. We also do not get polylogarithmic degree, but we do break the root and barrier. So okay, I will say what we get in a few slides. But let me describe the model of random graphs. So this model of random graphs is a random geometric graph. Here you have n vertices, v1, v2, up to vn, which are drawn from the unit sphere in d dimensions independently. And so your n vertices are, you should think of them as being random unit vectors on the sphere. And then you connect two vertices uh, with an edge if they're sufficiently close. Or equivalently, if the inner product between them is sufficiently large, larger than some threshold tau. Here I wrote tau of PD, denoting like it's chosen so that the edge between x and y exists with probability p. Okay, so this is your graph. I know I said something about triangle set, but uh, don't worry about that step. It's if you think of it in terms of like simplest to complexes. Uh, but okay, I guess so I would say this is probably the most important definition in this talk. So wait to see if people have questions about this.
So in step two you choose tau such that the probability is p. Is that what you're saying?
Yeah. So I choose a tau. Now the question is, given two random vectors, what's the probability that the inner product exceeds tau? It's gonna be some function of tau. But the smaller I make tau, the larger this probability is. So I'm gonna just like adjust tau so that this probability is exactly p. Okay, so this is like a model of random graphs, and now we're gonna try and analyze like the two-dimensional expansion properties of this model. But before we do that, like, why is this a reasonable thing to do? Like, I just like up here, it may just seem like a made-up model. So actually, let's try to understand what the distribution of a link in this model is. Like, let's say you have a vertex v. Now, if I take two vertices in the link of v, they're going to be two neighbors of v. They're going to be vertices u and w, which both have edges to v. And the question that I want to ask is, what is the probability that u and w have an edge conditioned on uh, the fact that they're both neighbors of v? And the point is, when you have like a geometric picture, uh, if I tell you that u and w share a neighbor, they're like going to be much closer on the sphere. So they have a much higher probability of having an edge compared to if they were chosen independently on the sphere. So if w and u were just chosen randomly on the sphere independently, like one would fall okay, let's just imagine the Earth. Like if W and U were chosen randomly on the sphere, one of them could fall in the Pacific Ocean, one of them could fall in Norway. But then if I like say, hey, actually, they both connected to um, Germany, then okay, like they both have to be like sort of in like one region. So that's why we expect like the density of within link to be much higher on average. So the links at least have a better chance of being connected, which is definitely a prerequisite to having two-dimensional expansion. So uh, now, but what I said was not necessarily anything special about the unit sphere. You could have had any other metric space, and you'd similarly have the property that if you choose a vertex and choose two random neighbors, they're much more likely to have an edge compared to two random vertices in the whole metric space. So maybe I can just give an example of a couple of metrics that provably fail. One of them is, let's say I take a graph and I connect all pairs of vertices that are distance 2 from each other. So then my link looks like this particular blue colored graph. Um, yeah, but this actually has issues. It ends up not working. Then similarly, instead of the sphere, you could think of like the torus with the L infinity metric. I mean, I just chose L infinity sort of arbitrarily, but this also doesn't work. And the reason why they don't work is actually somewhat fundamental, but I guess in the interest of time, I won't get into that. Okay, so now for the main theorem, what do we actually show about these random geometric graphs? So let's say you have n vertices, and you choose p to be this number, n to the negative 1 plus epsilon. Think of epsilon as being any small constant. Uh, okay, so I'm looking at a graph where the average degree is n to the epsilon. So it's not uh, constant degree. It's also not polylogarithmic degree, but it's still like much smaller than square root n. Then all of my links actually have expansion better than this half parameter. Namely, they have expansion half minus delta. And recall that because of the trickling down theorem, like because I've beaten this half barrier, I have spectral expansion that's 1 minus some constant. So maybe I'll again once again pause here to see if people have questions.
Like, does this delta depend upon epsilon, or are these independent?
This delta does depend on epsilon. So the smaller we want epsilon to be, the smaller we would actually be forced to take delta. Also the dependence is not actually particularly great. It's like delta is something like exponential and negative 1 over epsilon. So yeah, this is more so just sort of saying, yeah, you get like some slight gain. But I think to get like a random model that gets constant degree of polylogarithmic degree, we definitely would need to use a different model than the sphere. And I should say that this bad or okay, like getting stuck at polynomial degree like n to the epsilon, and also this bad dependence of delta on epsilon, they're not just artifacts of the analysis, they're actually sort of inherent to using the sphere. Okay, so maybe in the rest of the talk, I can try and give some intuition for the for how one proves this theorem. So in particular, I'll try to get into the structure of the link and why we should expect the link second eigenvalue to have this half minus delta parameter. So okay, here I put down a vertex V, and U and W are two vertices inside the link. One thing that is true in high dimensional spheres is that if I take any sphere cap, the sphere cap is simply I choose a vertex and then I look at everything that's within some distance of that vertex. Most of the measure, this cap, is concentrated close to the boundary. So actually, all the vertices in the link, we should expect them to be very close to the boundary. Like U and W are all are they like super close to the boundary. So actually, let's like mentally make this approximation that all the vertices in the link literally fall on the boundary. Now, what is the boundary of the cap around V? I claim.
This is just a property of high dimensional spheres, right? This is
Yeah. So if you look at this in like 3 dimensions or 4 dimensions, it's not going to be true. But if you think of the dimension as actually growing with the number of vertices, then you are going to get this property. Right. So the link. So okay. Since all of these caps fall very close to the boundary, we can actually think of the link as being a random geometric graph on a lower dimensional sphere, because the boundary of this cap is a sphere in one lower dimension. Maybe for intuition, just think of 3D. If I take 3D and I draw a cap and I look at the boundary of this cap, I get a circle. So I got a sphere, but in like one lower dimension. Okay, so the link is a random geometric graph in one less dimension in SD minus 2. So then the question becomes about what is a spectral expansion of random geometric graphs. Once we understand that, we can apply that understanding to the links which we are saying are lower dimensional random geometric graphs, and hopefully prove our theorem. Yeah, I'll see if there's a question here.
I guess we can continue.
Cool. Okay. Okay, all right. So here's what we can prove about the spectral expansion of random geometric graphs. Let's say G is a random geometric graph, and I'm going to use tau to denote like the inner product threshold. As long as the degree of the average degree of a vertex in G, which I'm denoting p times n, is much larger than polylogarithmic in the number of vertices, the second eigenvalue is actually roughly tau with high probability. So now remember that the links we said were some other kind of random geometric graph. They were random geometric graph at p times n vertices because p times n vertices are going to fall in a link. And the probability of two vertices having an edge is going to be some number q. We haven't yet said what q is. So let's try to understand what. So the same statement, when I translate it to links, is going to tell me that the second eigenvalue of the link graph is going to be roughly tau prime, where tau prime is the threshold for this connectivity Q. But now the question is, what is tau prime? Like we want to say that tau prime is less than half. So how do we get a handle on tau prime? And I claim that if the original random geometric graph had threshold of connectivity tau, then tau prime, which is the threshold of connectivity for the links, is actually this number tau divided by 1 plus tau, which you can verify is always smaller than half. And I will show you in a second why this tau divided by 1 plus tau number comes up. Okay, so yeah.
Yeah, so I'm a bit confused about the notation. So tau is your geometric graph and tau prime is the link graph. Is this the notation you're using?
Yeah, that is right.
Okay.
Yeah, tau prime is the threshold of connectivity in the link graph. And now I'm going to try and tell you what tau prime is.
Okay, sure.
Okay, so okay, now let's think of what's happening in the link graph. Let's say u and w are two random vertices inside the cap of v. So these are two random vertices in your link graph. So since they're close to the boundary of the cap, we can always write them. We can decompose them into a component that is parallel to v and a component that is orthogonal to v. So it's in this boundary of this cap around v. So it's going to be roughly tau times v plus square root 1 minus tau squared times something orthogonal to v, which in one case you're calling w perp, and in the other case you're calling u perp. And you can think of w perp and u perp as being unit vectors, both orthogonal to v. Okay, so now what's the probability that u and w have an edge in between? Well, the inner product of u and w still has to be at least tau. But now if we expand out what u and w are, we get this expression. And notice that so if I take the inner product of these two sums of vectors, I get four terms. One of the terms is going to be the tau v dot tau v. That's going to be tau squared. V is a unit vector, so it's tau squared times 1. Then there's going to be a cross term for tau v, for v dot w perp. But we said w perp is orthogonal to v, so that's 0. U perp is also orthogonal to v, so second cross term is also 0. And then we're going to get one more term, which is 1 minus tau squared times the inner product of u perp and w perp. And u perp, w perp, they're both unit vectors orthogonal to v. Namely, they live in one lower dimension. So the unit vectors, which are in one less dimension. So you should actually think of u perp and w perp as being the vectors in the random geometric graph that defines the link. Like the thing that we said is the random geometric graph in one lower dimension. Divide. We essentially get that the condition we get on U perp and W perp is that the inner product has to be larger than tau divided by 1 plus tau. So that's how the quantity tau of 1 plus tau comes up. So basically asking for U and W to be connected in the link is the same as asking for two random vectors in the D minus 2 dimensional sphere to have inner product at least tau of 1 plus tau, which we know to be smaller than 1/2. I'll see if there's a question.
I don't see any question on the chat. Sachin.
Okay, sounds good. Okay, so we established why like the tau for the link is less than half. So now actually the step that is remaining for us is to actually prove the statement that if you have a random geometric graph, then your second eigenvalue is indeed given equal to this inner product threshold. And for doing this, we're actually gonna obtain the statement as a corollary of a different statement, which is let's say look at the continuous graph, which is a sphere, and then I connect two vectors on the sphere with an edge if the inner product is larger than tau. So an example here is I pick one vector on the sphere V. Now everything with inner product at least tau is given in this red colored cap. So V has an edge going to all the vertices in this red cap. And the random walk that I look at on the sphere is any vertex just goes to one of its neighbors uniformly at random. So as you can see, like the random geometric graph is essentially some sort of a discretization of this continuous graph on the sphere. So there's going to be there's a technical argument that I'm not going to go over in this talk, which basically says that the theorem in blue, which is about the second eigenvalue of the random geometric graph, inherits its second eigenvalue from that of the full infinite sphere graph. And then the task for us becomes to analyze the second eigenvalue of the infinite sphere graph. And concretely, the statement about the infinite sphere graph that'll give us a second eigenvalue is what is the rate at which the random walk mixes? Like how quickly does this random walk approach the uniform distribution? And the thing that we showed this end is if you start with n probability distribution on the sphere and then start doing this random walk for L steps, then you end up roughly tau to the L close to the uniform distribution. And this is a statement that I'm going to try to give more intuition for in this talk. Whereas the chain connecting the statement about random walk on the sphere to the second eigenvalue of the discretization given by the random geometric graph is something that I won't talk about today. Okay, so now how does one try to show a statement of this sort? So okay, again, roughly what's happening here? Let's understand what's happening in one step of this random walk. In one step of this random walk, you have a vector v, and then you walk from v to somewhere in this gap. Again, let's think of going only to the boundary of this gap because that's where most of the mass is. So v goes to tau times v plus square root of 1 minus tau squared times u, where u is a random vector that is orthogonal to v. But now, for the sake of this talk, I'm going to make another simplification, which is, okay, well, this random unit vector orthogonal to V is like sort of a tricky object for me to think about. So I'll instead think of U as being a Gaussian vector. Again, in high dimensions, the norm of a Gaussian vector concentrates very well. So a Gaussian vector is really very close to a vector on the sphere. So see, maybe you should think of the Gaussian as being scaled by like 1 over square root d or something. But so let's actually think of this other process, and let's try to understand why this process mixes to like a Gaussian distribution. So what we're doing is we're doing the step where you go from a vector to tau times itself plus some scale Gaussian, but we're doing this L times. And when you do this L times, what's going to happen is you're going to get some coefficient in front of the original vector you started with, plus a Gaussian component. And the coefficient in front of the original vector you started with, you can see is going to be this tau number, the L times the vector V, plus some Gaussian part. So then we're interested in how that vector behaves. Like how quickly does this vector approach a Gaussian distribution? So let's draw like a one-dimensional cartoon to see what's going on. So the red curve, think of this as the distribution you ended up at after L steps, which is you're basically a Gaussian. Like you have like a slight non-Gaussian part, which you can think of as a mean. This tau to the L times V, but then you're adding like a random Gaussian thing to it. So it's basically a Gaussian with mean tau to the L times V and a covariance matrix given by 1 minus tau to the L times identity. Whereas we're interested in how close this is to an honest to goodness Gaussian, which is an zero identity. And in one dimension, these two things are actually really close. Like the statistical distance between these two scales as this number tau to the L. So this is the intuition for why this walk mixes rapidly. I guess the actual proof is like a bit more complicated, and it's proved by relating this walk on the sphere to some sort of Brownian motion process on the sphere. And one step of the discrete walk is approximated by a certain amount of time of running Brownian motion. But I guess I won't get into that. And I hope the intuition about like why doing this walk in Gaussian space mixes conveys why it also mixes on the sphere. Yeah, now I'll see if people have more questions because I'm pretty close to being done with the technical portion of my talk.
Can you go a slide back? Slide or 2 slides back?
Yes.
One slide back.
Yeah. Is this slide okay, or should I go further back?
No, means trying to understand this green statement.
Yeah. Okay. I can try to break it down.
Yeah, sure.
Okay. So this is basically saying the following. Imagine the random walk, or imagine the following distribution on the sphere. So I have some crazy distribution alpha. I don't know what alpha is, but it can be anything. So I sample a vertex V according to alpha, and then what I do is I walk from V to a random vertex inside the cap of V, like inside the red region. That's one step. But then I keep doing this. I do this L times.
Okay.
Now the question is, after I do it L times, okay, I've ended up somewhere, but what is the probability distribution of where I have ended up? Is it uniform? Is it far from uniform? And what this statement is saying is that it's actually pretty close to uniform. Like this total variation distance
I see.
is is close to uniform. And how close is it? It's like roughly tau to the L close. Okay, the other stuff like, okay, it's 1 plus little 1. Yeah, don't worry about it. And this square root half log 1 over p, that's also like some other technicality. So you should really only focus on the tau to the L term.
Right.
Did that clarify things?
So the variation distance bounded by tau to the power L, what does it say about the spectral gap of this continuous gap?
Right. So yeah, okay, maybe this is something I should have like said more explicitly. If you can prove that your total variation distance decays at a rate like say something to the L if you take L steps, okay, like tau to the L if you take L steps, then it says that the second eigenvalue is at most tau. Like basically giving a rate at which the total variation distance decays uh, also gives you a control on the second eigenvalue.
Yeah.
Yeah. Okay. This is definitely something I glossed over and should have clarified better. But that's why you're able to say that the second eigenvalue of the sphere is tau.
Right. Yeah, we can go ahead.
Okay. And the Gaussian intuition made sense for why we should expect like a rate of tau to the L in terms of how quickly
Yeah,
you get close to.
yeah, that makes
Okay.
sense.
Okay. Okay. All right. Actually, yeah. Okay. So I'm actually done with the technical portion of the talk, and I just wanted to state like a couple of further questions. So here, a lot of stuff that we did in this talk were very catered to the sphere. Like we said, oh, the length in a sphere is a cap, but a cap has most of the mass on the boundary, and that is a lower dimensional sphere. So we really exploit the self-similarity property. But what is it about like a particular geometric object, like a manifold, that tells you whether you get a two-dimensional expander or not? And in particular, are there other manifolds that can break this n to the epsilon barrier that we ran into for the sphere? Like, can you get polylogarithmic or constant degree if you change the manifold that you're using? So this is one question that I'm very interested in. And another is here, I talked about like two-dimensional expanders in particular, but maybe you could ask about like 3 dimensions, 4 dimensions, and so on, or generally k-dimensional expanders. Like what's the situation there? And yeah, that's it. That's it for the talk.
So your results are, I thought for simplification, you are presenting two-dimensional expanders, but your results are, do they give anything for k-dimensional expanders as well?
No, they don't. They our results are only for two-dimensional.
I see.
Yeah, no. The simplification was so here's the thing. Like normally when people talk about two-dimensional expanders, you're thinking of uh like 3 uniform hypergraphs. So
Right.
here you should actually think of each triangle as being like a
Yeah.
three area hyperedge. Each triangle
Right.
that occurs in the geometric graph as being a 3 area hyperedge. And then the
Right.
graph that is expanding is some weighted graph where each edge is weighted by how many triangles it participates in.
Right. Sure. Yeah.
So that's like the thing that I swept under the rug a little bit.
Right. You mean like the induced distribution on the levels of the HDX set?
Yeah, exactly.
Yeah. So there are like these other kind of walks. So in HDX you don't have you have some equivalents, but these are not exactly the same thing. Like this notion of expansion, and then you're doing these up-down walks. So can you say something about that as well using this?
Yeah. So I guess because this is a two-dimensional expander, we do get rapid mixing of the edge triangle edge walk. Like that actually follows from link expansion too. So
Oh, because you have the 2R loss, and for you R is 3.
yeah.
Okay. See. Right.
Yeah. Actually, do you think about these kinds of things like high dimensional expanders, their properties, and like up down box?
Right. Yeah. Uh, Sorry, I didn't hear
Oh no,
you.
no, I was asking whether that's what you work on.
Yeah, yeah. That is something that I do work on. I have worked on, and I do plan to work on in future as well. I think
Okay,
I'll
very
stop.
cool.
I don't see other questions. I'll stop the recording and we can have a more informal discussion.
Okay, sounds good.